Good afternoon, class. Today we'll finish up virtual memory. Today's topics are memory mapped files, allocating kernel memory, other virtual memory considerations, and we'll look at Windows and Solaris examples. One last time, here are the chapter objectives. File I/O is expensive time-wise because we have a system call and then we have to work through the file system. So mapping files into memory space is a win, because then we can access the files directly through the memory system without having to deal with overhead from a system call. So of course initially we will have a page fault as the portion of the file that we're accessing is brought into memory, but then the subsequent file operations are treated as memory accesses. One of the issues is when written data makes it back to disk, given that disk storage is expected to be permanent storage, and memory, of course, is temporary storage. So data can be written back periodically when, as the pager scans for dirty pages to write them back. The data will definitely be written when the file is closed. A Linux process can explicitly request that a file be mapped into memory via the mmap call. Some operating systems, as mentioned there in the first bullet, use memory mapped I/O for all files. Solaris is an example. It's not uncommon for even if the user process is not using memory mapped I/O, for the kernel to actually map the I/O internally for a user process in order to more efficiently provide the data to the user process. So here's an illustration, and also note that processes A and B here are utilizing shared memory on top of the memory mapped I/O. And here's a cleaner illustration of that concept. I'll skip this slide. Kernel memory allocation is treated differently than user memory allocation for two main reasons. Kernel memory requests can be of various sizes and occur quite frequently compared to user memory requests, and in order to avoid internal fragmentation, kernel memory allocation requests are treated differently, and it's also the case that large kernel memory allocation requests can have the requirement that the memory be contiguous, as opposed to user memory, which remember the page frames can be spread throughout physical memory. Linux originally used the buddy system, so starting from a contiguous memory segment of some length, some power of 2 length, when a kernel memory request is made, that request is rounded up to the nearest power of 2, and then if necessary, the pre-allocated memory is split in order to satisfy the request. So in this example, if there's a 256 KB chunk available and the kernel requests 21K. Well, that 21K will be rounded up to 32K. The 256K is broken into two buddies, 128 each. One of those buddies is broken up into 264K, and one of the 64K is broken into 132K, which will be used to satisfy the 21K request. Using the buddy system in this way allows us to recombine or coalesce adjacent free chunks into a larger chunk. Of course, the disadvantage here is fragmentation. So here's a diagram illustrating the buddy system. So Linux gave up the buddy system for slab allocation, which, if I recall correctly, is also what Solaris uses. So the idea is that there is a distinct cache for each different kernel data object type, and objects are allocated out of their corresponding cache, and then a number of slabs are used to provide the actual storage for each cache. So as mentioned here, the cache is backed up by one or more slabs, where a slab is physically contiguous pages. In the benefits mentioned here, no fragmentation, because for each slab a number of kernel data objects are allocated, and we have fast memory request satisfaction, because each time we allocate a new slab to one of the caches, that gives us a number of additional free objects to use as they're later requested within the kernel. All right, so here's an example. Let's consider these just for sake of argument. That this is a cache for PCBs, and this is a cache for file handles. So these are actual PCBs that are mapped through the cache into slabs. If a fork call were made and we needed to create another PCB, well, this empty cache entry here could be allocated and the storage backed up from the slab. If all of these cache entries were full, then another slab would be allocated, giving us more cache entries. So note that several of the PCBs are stored per slab, minimizing fragmentation as much as possible. And due to the fact that each time a slab is allocated to a cache, we get a number of new free cache entries. That implies that the allocation of new PCBs will be fast, because all we have to do is search the cache for an empty PCB entry and then allocate it. It's only when the cache is completely full that PCB request takes longer, because we'll have to go out and allocate a slab to the cache. All right, I don't see anything additional to comment upon in this slide, and I won't comment upon anything here either. So remember, the principle of demand paging is that a process's page is not brought into main memory until it is actually requested by the process. That, of course, implies that when a process first starts up, that it's going to incur a large number of page faults. So a technique that can be used to reduce that is to pre-page by actually bringing in pages before they're requested. Of course, if we bring in too many pages, and some of them may be unused, and then we have a trade-off calculation to perform. Often page size is dictated to us, but in some circumstances we get to choose the page size, and the issues that need to be taken into consideration include fragmentation. For a larger page size, we have more internal fragmentation. Right? Remember, on average, the size of a fragment is half the page size. Page table size also comes into play, so the smaller the page, the larger the page table. Resolution is the notion that the page should be just large enough to bring in the memory that the process requires at that point in time and no more. I/O overhead, the larger a page, the more data that has to be transferred between memory and the paging device. Number of page faults, locality, and TLB size and effectiveness come into play. So TLB reach here is the amount of memory accessible from the translation look-aside buffer. So that's going to be the number of entries in the buffer times the page size. And ideally, the process's entire working set will fit into the TLB. There won't be a higher degree of page faults. What will happen is that there will be more TLB misses if the working set is not in the TLB. Program structure can come into play. In this example, this is the row offset of a two-dimensional array in C. This is the column offset. So the row elements are stored contiguously. So row 1, row 2. So if we walk through an array by columns, as is being done here, and we have a situation where each row is stored in a page, then we'll incur, we could potentially incur a page fault for every single array access, because each subsequent array access is to a separate page. Whereas if we simply rearrange the indexes so that we're accessing adjacent rows on each memory access, the inner for loop, each time the inner for loop executes, it's only accessing a single page. So we could incur just a single page fault each time I increments, giving us a far lesser number of total page faults. This question of having to lock pages into memory due to pending I/O is something that we've discussed before. Obviously, if there were a pending read or write from disk to particular pages in frames, the swapper had better leave them pinned here until the I/O completes. So let's briefly look at Windows and Solaris examples. So Windows uses this notion of clustering, which brings in pages surrounding a faulting page as a kind of pre-pages. And note that when the amount of free memory in Windows falls below a certain threshold, then the working sets are trimmed in order to increase the amount of free memory. So Solaris has a page out process that uses a modified clock algorithm, in order to help to maintain a certain number of free frames. So when there's lots free memory, paging begins. Desired free is a threshold. So desired free is less than lots free. When desired free is reached, the paging rate increases, and then min free is even less than desired free. When min free is reached, entire processes begin being swapped out. And then the scan rate here is the rate at which pages are scanned by the clock algorithm. So the increased paging is affected by moving from slow scan towards fast scan. So here's a graph illustrating it. So here we have the amount of free memory and the scan rate. So if we reach lots free, then the page out process begins to run slowly. But then as we approach desired free, you can see that page out scans more quickly. And then remember, when min free is reached, that's the point at which processes will begin to be swapped out. All right, so that finishes chapter 9.